So you're seeing the trend by now that we have these three parts. There's one more paper that I want to talk about as the data talk today. This one's a little more involved because the previous ones were periodic trends and papers that reflected periodic trends. This is one that reflects thermodynamics and applies it to the biggest stage possible, applies it to the universe. So we're going to start with the timeline that the universe began with the Big Bang. There was energy and there was light. The light condensed into atoms. The atoms clumped together and cooled down. And usually I just go on from there. But you could raise your hand at that point and you could say, why did they cool down? Why didn't they heat up? Or why didn't they do something else? You know, why do we have the thermal energy changing as opposed to work changing? I mean, you can even talk about expansion work and things like that, the concepts that we've had. So always ask the why question. I can't promise that we can always answer all the why questions, but sometimes, like with this question, we can actually answer it with physical chemistry equations. And the answer has to do with entropy. And so I just want to say that we've established that entropy is a number, and you can make jokes about this because a lot of times we refer to entropy as disorder, but disorder is not a number. So disorder is only a partial metaphor. If you look at my desk right now, I think I'm off the chart right now. I really need to clean up my desk. But when you start grad school, this is Piled Higher and Deeper comics about when you start grad school, you have a clean desk and you're like on top of things. And then year 2, things get a little more complicated. Year 3, you can't find your monitor. And your PhD year, which is year 4, 5, 6 maybe, you're piled under this. And this is where I have stayed ever since. It's kind of funny to read this. This is kind of like hearing Atkins talk about a desk, okay? Because he's saying that desk entropy is a fake word quantity that measures a workspace's degree of disorder. So realize that this is, the joke here is that you're putting a quantity on disorder. But we already said, because of the third law of thermodynamics, you can put a quantity on entropy. And that's why this disorder metaphor only takes you so far. How do you really put a quantity on this? You could maybe massive stuff on your desk, but that's an imperfect kind of quantity. So disorder is only a metaphor, and entropy equals spreading out. It kind of works in that case, but we want to really get down to entropy. If we want to apply physical chemistry equations to things like the universe, we've got to deal with numbers. Equations require numbers. So how can we talk about the universe's entropy with numbers? Now entropy, remember that entropy can decrease in the system if it increases in the surroundings. Added together, the entropy always must go up. The delta S for any spontaneous process must be positive. But the good news is it can go up in the surroundings and down in the system. And there's actually a paper that has an example about how this happens, like in crystallization. If you ever think about crystallization, that's order forming, right? What the second law says is if you see a crystal forming, there must be more disorder, more spreading out in other parts in like the surroundings of the crystal. So like the crystal does the opposite of spreading out. It comes together. And this actually talks about where is the entropy when you have a crystallization event. Somewhere in the surroundings is the answer. But how do we apply this to the universe? By definition, the universe has nothing outside it. So if the entropy of the universe, if the universe is always spreading out, why would any of it ever come together? After the Big Bang, why did anything come together? So we can't solve this problem by appealing to the surroundings. If our system is the universe, we can't do the usual answer of saying that the surroundings are where the entropy actually goes up. So, but the thing is, we can still apply, sometimes people will say, well, we should just throw out the equations. We actually can still apply the laws of thermodynamics, and even though the universe is incredibly complex, it's actually simple enough and elegant enough that we can look back and we can recreate with the laws of physics all of these steps of creation, the steps of the Big Bang, the steps of galaxies forming and stars forming, the steps of stars making the different elements. And we're actually very successful to this. This is a paper about how you might hear that and you might think, okay, it's like equations like a book this big or something like that. But it's actually surprisingly few equations. Scientists always come back and they're like, you know, these equations work unreasonably well. There's lots of good quotes about that. Because physics works. You know, physical chemistry also works. So you can actually follow some of this. These equations are simple enough that after just 2 chapters of PChem, we can talk about a few of them. And that's what this paper is about. This paper refers to one of these papers. And this actually refers to a couple of other concepts. We can't completely describe the universe yet, but you'll actually be a lot closer at the end of this class. You can actually look at this paper, and you will see equations that you understand. And this is kind of cool. They use basic physical arguments, which are physical chemistry, and they determine what the masses and sizes of important objects in the universe are in terms of just a few fundamental constants. In other words, just a few equations, and you can calculate, like, how big should a star be? How big can a planet be, a rocky planet? How big can a galaxy be? So we'll see how these, and they talk about, like, the Planck mass and the Chandrasekhar mass. We don't talk about that. That's too physics. That's too astronomy. But we're actually pretty darn close to actually talking about those things. 8 pages later, and it's just 8 pages, they say that you can write these equations. They actually express it as one equation, equation 26. The mass of a rocky planet is this equation. The minimum mass of a star is the next equation. The maximum mass of the star is the next equation. These are no worse than the equations that I inflict on you, okay? The equations that you do for your homework. So the mass, and let's see, the maximum mass of a white dwarf, the maximum mass of a neutron star, the minimum mass of a neutron star, and the characteristic mass of a galaxy. So yes, they even calculate like what the average galaxy looks like. To be sure, there are tons of exceptions. There's tons of complexity. But you can fit this on a t-shirt. I mean, you can fit this on a 3x5 card. I wonder how successful you could be going into an astronomy, physical astronomy class with this on a card and answering the questions. You probably would still fail. You know, if I did that, you know, I'd probably fail. But still, I think I would get some things right. I would get the expected mass of a rocky planet right from a calculation that you can do on your calculator. So they express the basics of important astronomical objects with only 5 constants. Okay? So for only 5 constants, you can get all these masses. There's a book called Only 6 Numbers by Sir Martin Rees that talks about this on the universal Big Bang kind of scale, which I am not qualified to talk about at all. But all I can say is I can look at those and they look recognizable, right? Okay. So there's one other thing that we want to do as we go through. We want to apply these 2 equations. We want to apply the equations to a reaction that is space itself spreading out. None of our equations so far can do that. But we also want to apply the concept of entropy, which we have talked about, to the reaction that is the Big Bang, space spreading out. To do that, we have to look at entropy a slightly different way. I just want to remind you that on the very first day of class, we introduced this equation. And what I've done is that it shows up in every chapter, but I haven't mentioned it till now. So I'm going to go back and I'm going to say, okay, we calculated, Atkins showed you on the first day of class that you can calculate the relative population of 2 states just by knowing the energy difference between them and the temperature. The temperature tells you how many are going to be in state 2 minus state 1. We pointed out that that was an e to the negative x function. And so the thing is, you can have the different ways that a molecule can move, the different things that can move. It's really a movement. It's work, in a sense. If you have a molecule moving, there's a force applied over a distance. There's 1/2 mv squared. There's physics to that. And there are energy levels that are set. The only real difference is when you're talking about an individual molecule, the energy levels can't just be anything. The energy levels are quantized, especially when you're talking about electrons. But that's really cool because if we have quantized states, we have an N1 and an N2 value. And we can talk about how many electrons are at the higher level, how many electrons are at the lower level. And we can do that for molecules in different energy states as well. If something is moving and it has a mass, we can apply these equations to it. And so that means that, remember when we talked about heat capacity, we talked about temperature as being random motion, right? Random motion of the molecules. And the heat capacity is something that takes that energy, that joules of motion, and turns it into Kelvin, you know? Heat capacity translates between the two. You can also talk about heat capacity in terms of energy levels, okay? So you have two heat capacities here, and the only thing I don't like, Atkins squeezes these into the margin. So they're really hard to read. That's why I want to explain it to you in person, okay? This is comparing two substances with different heat capacities. And let's take it to extremes. Let's say that the substance A is a solid and substance B is a gas, okay? The heat capacity is going to have the gas is going to have a very low heat capacity, and the solid is going to have a very high heat capacity. And you can actually explain that with energy levels if you say the high heat capacity solid is going to have very close together energy levels. The low heat capacity gas is going to have very far apart spaced energy levels. So the gas is going to have more energy levels. If you take the Boltzmann equation, remember the Boltzmann equation tells you how many are in which level. It compares two levels, but you can actually do like an integral and stuff like that to compare it over as many levels as you want. And the Boltzmann equation depends on temperature and the spacing of the levels. So if you have two temperatures, let's see, this one's actually blue. It doesn't show up very well on this way of showing it, but the red sort of shows up. When you have it at a colder temperature, you have the blue line of population of energy levels. The farther to the right, the more atoms are in that energy level. The red line is when you heat it up. So if you take the Boltzmann distribution and you take something with a lot of squished together energy levels and you heat it up, you have it cold at blue, and then you heat it up, you're going to end up with more atoms higher up. You know, you're giving energy to the substance. But because there are so many energy levels close together, you push some up, but you push them up into very close adjacent levels, and they fill up those levels, and then you don't get as much of a change when you change the heat energy, when you change the temperature. When you change the temperature, you don't get as much of a change in the energy population. But with the gas, it's the opposite situation. When you have, if you add energy in, you increase the temperature, you push some atoms up into the higher energy levels where they're moving faster. They're still, you know, on average moving randomly, but they're moving faster now. Because the energy levels are wider spaced, there's no room for them. They get pushed up actually a few of them get pushed up to higher energy levels sooner. So what this shows is that for the gas, you get higher energy levels for the same temperature change. And that is what we calculate as a low heat capacity, because you have a little temperature change and it has a bigger change in their motion, a bigger change in the kinetic energy. Same temperature change, they move around much less. And you can think about this, solids are usually heavier, right? Like a chunk of uranium has a lot of neutrons. It's very heavy and dense. That will have a higher heat capacity than a gas or a liquid, okay? So this reinterprets heat capacity in terms of energy levels. And Chapter 2 talks about something we talked about. We talked about how volume, when you increase the volume, you increase the entropy of something if you're keeping the temperature constant. The way to think of it is, you know, everything, if the temperature is staying constant, when the volume increases, it's harder for them to, they have to be moving faster to reach the same temperature, or they don't hit the walls as much. There's two other ways to explain it. So actually, but talking about it with the concepts that we have already is actually kind of difficult. It's a little bit difficult for me to explain why does increasing V increase S using the tools that we've already introduced. But actually, if we start to think about energy levels and spacings, if you have energy levels in a small container, and then you have the energy level, the same gas in a larger container, so V has increased here, The energy levels, just like the strings in the quantum mechanics actually, they get stretched out and they stretch together more. They get stretched out and sort of compressed because in a sense, the energy levels are allowed to spread out more. And they go down because you can think of it as sort of a conservation of energy type thing. That means if my temperature is constant though, the total energy stays the same. As I increase these, I have more levels that fall under the total energy given to them by that temperature. In other words, I have more levels being populated if I increase my V, and I keep my T constant, there's more levels for the gas to be at, okay? It's really important to keep in mind constant T. That's a huge part of this. But this is still not the best way to explain it. We actually need a third way to explain it to really understand why increasing V increases S. And that's this spatial entropy metaphor. And this will really help us to say what is the entropy change of an exploding universe. Okay? So you start with this by thinking of probabilities. Let's say that we have a box, and the box only has 4 spaces in it, okay? And we have 2 marbles in the box. We close the box, we shake it up, and we open the box, and we see where the marbles are. And we're only measuring one thing. Are both marbles on the same side or not? Are both marbles on the left, or are both marbles on the right? Now, if I write out all the different possibilities, I can write it out like this. And the marbles can't overlap. You know, they're like regular marbles in that sense. So, and you can already see this is like atoms in a container, but at a very simple level. If I do that, what am I most likely to see? If I open up the box, there are 2 ways that I can have both marbles on the same side. But how many ways are there to have both marbles on opposite sides? Opposite, 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 opposite. So we actually have 4. Yeah, this one counts because all that matters is on the dividing line. Are they on either side of the dividing line? 2 ways to be together, 4 ways to be apart. So even without any other bonds or anything, this is just marbles in a box. The probability, it's like rolling the dice, but it's like 4 of the dice sides will give you things apart, so you're twice as likely to find them apart than together. This is also about entropy, okay? The particles are 2 times more likely to be spread out, and we would say that the spread out state has more entropy. They are more spread out when they are both on opposite sides of the box, okay? So this is actually related to the entropy. The fact that there are 4 ways to be spread apart but only 2 ways to be together can be expressed mathematically as a probability. And there's this equation, which is simple on the surface. What it is that entropy is related to a constant times the number of microstates available at that energy level. So this would be, there are 4 spatial microstates available for the balls to be apart. There's only 2 spatial microstates available for the balls to be on the same side of the box. So that means that the entropy would be times 4 for the apart case and times 2 for the together case. Entropy would be twice as high. Now we're dealing with numbers. We're dealing with volumes, and we're dealing with numbers that we can calculate. And realize that microstates can be thermal as well as spatial, and all the entropy types actually go together. But some of them are better for answering some questions than others. This is the one that helps explain what happens to the universe. So we can ask the question, why does the matter cool, or where does the energy go? The energy goes into entropy, in a sense. There's a conversion factor, but you can say it goes into dispersion, it goes into configurational entropy, it goes into the fact that there are more ways to be spread apart than there are ways to be together. There are more ways to arrange a bigger matrix than a smaller one. Imagine doing the same calculation that we did. We did the calculation of 4 versus 2. We can do the same calculation for a larger box with all these, like 1,000 places for the marbles to be. And then we can have the marbles like all start out in a corner of the box. We can shake it, and open up the box, and you can pretty much guess what will the box look like. You can't guess exactly where each marble will be, but you can guess that this is probably pretty close. This is closer to what the box will look like. There are more states that look like this than there are states where all the balls are in one corner. There are only 4 states where all the balls are in one corner, for instance, as opposed to thousands or even millions of states where they are spread out. So again, no chemical bonds. We're talking about configurations, and we're talking about what's randomly likely to happen, but that's a measure of entropy. The state that looks like this has a higher entropy than a state that they're all collected in one corner of the box. So a bigger matrix has more configurational entropy, and they can actually write an equation for this. The delta S for configurational entropy equals our gas constant times the natural log of VF over VI. This looks like one of our equations. But this is a microstate entropy equation. But you can see we're dealing with pChem concepts now. So that is the entropy of expansion. And then you can also think that, well, there's other kinds of entropy. What about entropy of them staying in one place? You know, that's an entropy of movement over space. What about entropy? Each of those marbles could be hot or cold. And if you think about it, okay, so we've already talked about how these are all forms of energy, and the energy can interconvert. So molecules can vibrate, rotate, they can move electrons up and down, they can do all these motions while staying in one place. And that's what we call heat energy. So it's these kind of motions, the motions that don't move in a particular direction are expressed as heat, okay? So the thing is, we want to ask how many thermal microstates are accessible. If the marbles can be different temperatures, how do the temperatures arrange themselves? And actually, you have a very similar equation. Delta S for thermal entropy is our friend the heat capacity times the natural log of TF over TI. So again, we see a very similar equation, and deep down they're both different facets of entropy. It's just a question of, are the molecules moving in a direction, or are they sort of rotating in one place? Are they spreading out over a volume, or are they essentially staying in place? We label one thermal entropy, the other one configurational entropy, but they're both entropy with different proportionality constants. One's dependent on temperature and the other's dependent on volume.